Hi everyone. Today I will present our work, Infiniswap, which is an efficient memory disaggregation system over RDMA network. Infiniswap can transparently expose the free memory inside the cluster to users' application. And in general, it improves clusters' memory utilization, and also it can bring benefits to application's performance. This work is done by me with my colleagues Youngmoon, Yiwen, and our advisors Mosharaf and Kang. I will start from why we built Infiniswap. Memory-intensive applications are widely used in many places, like low-latency service and data-intensive analytics. Those applications work very well if their working sets can be totally fit in the physical memory. However, if those applications cannot get enough memory from their host machine, then part of the working sets will be put in the swap space by operating system. And normally, the swap space is a local disk. And therefore, there will be some performance degradations on those applications. But how much performance will be lost in this case? And here, we select 4 different memory-intensive applications. The first 2 are latency-sensitive ones. Their performance can be measured by the median or tail latency of their operations or transactions. In VolDB, we run TPCC as a workload. And for MinCached, we select a Facebook workload. The other 2 are throughput-sensitive applications. They work on large datasets, and their performance can be measured by the completion time of their tasks. For Power Graph, we run TankRank from Twitter. And for GraphX, we run PageRank as the workload. So those blue bars show the normalized peak performance for each application when they have enough physical memory. And also, we capture the peak memory usage for those applications, and this will be used as the size of their working sets. And next, we shrink the memory size for each application. So only 75% working sets for those applications are in the physical memory. As we can see, for VolDB, its performance drops disproportionately since we only removed 25% of their memory, but its performance drops over 80%. And this also happens for MinCached. Its remaining performance is less than 50% of its peak performance in this case. If we remove another 25% memory from those 25% memory from those applications, and then the remaining performance for those 2 applications are totally unacceptable. So for throughput-sensitive applications, and we surprisingly found those 2 applications work very well on the 75% memory constraint. But if we remove another 25% memory from those applications, then their performance will be as bad as the others. And this issue has been widely observed by the users of those applications. So most of the time, people will overestimate the memory requirements of those applications for better performance. But this is one of the major reasons for the memory underutilization in the cluster. These 2 figures show the allocated memory versus user memory over Google cluster. As we can see, most of the time, the cluster's memory, over 80% of the cluster's memory has been allocated to applications. However, the actual memory usage is lower than 50%. So we have large portion of memory which has been allocated but not being used. So the problem is, can we utilize this part of free memory? And also, in the cluster, different machines can have different memory utilization. And in this example, machine 1 has used up all its memory, but for machine 2 and machine 3, they still have large portions of free memory. In existing cluster, machine 1 cannot get the free memory source from other machines. And to solve this problem, people have proposed to do memory disaggregation over fast networks inside the cluster. In this design, the memory disaggregation layer can expose a global memory bank to all the machines in the cluster, so that machine 2 and machine 3's free memory can be used by machine 1. But to make this idea being practical, we are still having many challenges. The first one is how to minimize the deployment overhead. So this memory disaggregation system should be applicable to existing hardware and applications in the cluster. And also, running inside the cluster, this system has to tolerate failures such as network disconnection and machine crash. And the most important challenging is how to make this design scalable. And actually, the idea of using remote memory has been proposed for more than 2 decades. And in recent years, with the development of fast networks, it's attracting more and more attentions from multiple communities. In computer architecture, they have designed the memory blade, but this system requires coherent support from new hardware. And in HPC community, they have high-performance block device, which is called HPBD. But this system brings no fault tolerance feature, and also it is not scalable to a cluster. And in system community, we have many RDMA based key value service systems, such as herd and farm. But to apply those systems, applications have to be modified. And in industry, Intel has proposed their rack scale architecture project, but this work also includes many modifications on hardware. And therefore, we built Infiniswap. It can satisfy all those requirements. Now let's see how Infiniswap is designed. This is the overview of our system. We have 2 major components, Infiniswap block device and Infiniswap daemon. For machine 1's operating system, the Infiniswap block device is just a regular swap space. But inside this block device, we have a request router. It can forward swap requests to different destinations, either the local disk or remote memory, based on the status of the remote mapping. And under this block device, we have a local disk. It can asynchronously back up the swapped out data from our block device. By having this local data copy, our block device can tolerate failures on remote memory. The Infiniswap daemon has to maintain a local memory region so that it can provide remote memory service to the block device. All the components in Infiniswap are connected by RDMA network. By using the one-sided operation provided by RDMA, components can do data transmission without the involvement of remote CPU. And in summary, those 3 design objectives can be satisfied by using the system we just described above. But inside the cluster, a single block device can get remote memory from multiple daemons. And likewise, a single daemon can provide its memory to multiple block devices. So here we are facing the challenge, how to scale remote memory. Or in more detail, we can ask how to find the remote memory in the cluster. And when the remote machine cannot provide so much remote memory, which remote mapping should be evicted. And to satisfy this scalability requirement, we designed a decentralized approach in Infiniswap to do remote memory management. As we all know, local memory space is managed at page scale. But if we also divide the remote memory into small memory pages, then we have to use lots of space to maintain the metadata for remote mapping. For example, if this block device needs 1 GB remote memory, then it has to maintain 256 kilo entries in a remote mapping table. And also, it has to do the same number of round-trip communications to look for remote memory. So to reduce this overhead, we aggregate small memory pages into a very large memory slab. And in our current implementation, it's 1 GB. And therefore, the swap space in block device and the memory region in daemon are divided into multiple slabs. When a slab from block device is looking for remote memory, we have to pick a remote machine very carefully because higher memory utilization at the remote machine side will generate more slab evictions, and the slab eviction will have create performance degradation on the block device side. So the goal in this selection is to balance memory utilization across all the machines in a cluster. If we can have a centralized controller who has the knowledge of all machines' memory status, then this selection will be very easy. But centralized design brings many problems, such as single point failure and limiting systems scalability. Therefore, we turn to decentralized approach. Here, we use power two-choice algorithm to select a remote machine. Every time, we will randomly query two remote machines' memory information, and we will pick the one with lower memory utilization to build the remote mapping. Now let's look at the other side to see how memory slabs are evicted by Infiniswap daemon. When a remote host needs more memory for its local applications, its Infiniswap daemon has to return some memory slabs back to its host machine. And this eviction starts from the unmapped slabs. And sometimes this Infiniswap daemon has to evict some mapped slabs to release the memory pressure on its local host. And considering the performance degradation caused by slab eviction on the block device side, we have to select the least active slab to do the eviction. But the problem is we are using one-sided RDMA operation, so the daemon does not know the swamp activities of those mapped slabs. And also, it will be too expensive for daemon to query the swamp activities of all those mapped slabs. To solve this problem, we use power multiple choice algorithm. If we want to evict E slab, then we will randomly pick E plus E prime slabs. After we got their swamp activity information, we'll do the eviction on the E least active ones. And in this example, if we want to evict one slab, we will randomly pick two of them, the first and the third one. After we got their swap activity information, we'll evict one with fewer swap activities. And in terms of implementation, Infiniswap block device is a loadable module running inside the kernel, and the Infiniswap daemon is a user-level process. For each pair of active block device and daemon, they have a single RDMA connection, and this connection is shared by the control plane and data plane. Before we talking about the evaluation, let's see what are we expecting from Infiniswap. The first one is application's performance when part of its working sets are in the remote memory provided by Infiniswap, and also how much memory utilization of the cluster can be improved by our Infiniswap. We also have evaluated Infiniswap in many other aspects, but in this talk, I will just focus on the first and the second one. We evaluated Infiniswap on a 32-node InfiniBand cluster, and each node in this cluster has a 56 gigabits per second InfiniBand NIC. We run those 4 applications in this evaluation. Firstly, we compare the application's remaining performance when half of their working sets are in different places, the traditional swamp space, which is the local disk, or the remote memory provided by Infiniswap. We have seen these results at the beginning of this talk. So in x-axis, we have 4 different applications, and the y-axis is the normalized performance for each application. And when the application using remote memory to place its working sets, their performance can be improved by 2 to 60 times comparing to the case when application using the traditional swap space. And our minimum performance improvement is from graph X. When this application is running, it generates many swap bursts to access remote memory, and this makes the local disk being the bottleneck of our system. Next, we run 90 containers in the cluster, and each container has a single application. This figure shows the memory utilization of every node in the cluster. After applying Infiniswap, almost every node's memory utilization has been improved. And in general, the cluster's memory utilization is improved from 40% to 60%. And so right now we found there are still some limitations in Infiniswap which has not been well addressed. And currently we are working on those issues. The first one is a trade-off in fault tolerance. We have a local disk to tolerate failure from remote memory. But this local disk can be the performance bottleneck of our system in some cases. And we are considering to maintain multiple data copies in remote memory to replace this local disk. But maintaining multiple data copies will greatly reduce the space efficiency in remote memory. The second issue is performance isolation among applications on the same host. Because in Infiniswap, it cannot limit remote memory usage for each application. And also, it has no knowledge about the mapping between remote memory and application. And in general, Infiniswap cannot limit who uses how much, and also it does not know who is using which. So their applications can have interference between each other, and this makes their performance unstable. In conclusion, we have designed our system and implemented our system. Infiniswap is a remote paging system over RDMA. It can improve applications' performance and also increase clusters' memory utilization. And currently, it's one of the most efficient and practical memory disaggregation system because it's applicable to existing hardware and applications in the cloud, in the cluster. And more importantly, it can tolerate failure from remote memory. And also, it can do remote memory management in a decentralized manner and works well at scale. And thank you. I'm happy to take questions.
Yeah, I'm Wonso from NetApp. So you mentioned that you use 1 GB slab size to reduce the metadata overhead. So does it require that 1 GB of contiguous memory space before swap? And then, or actually, are you using any periodic defragmentation to avoid that?
Yeah, thank you. That's a very good question. So this 1 GB remote memory should be contiguous memory region, and that should be at the Infiniswap daemon side. And yeah, so what's the next question?
So that how could you guarantee that you have always have the 1 GB of like contiguous memory space? Do you actually run the periodic defragmentation on every host that you can have the contiguous memory block?
Oh, thank you. Yeah, so at the Infiniswap daemon side, it will pre-allocate this 1 GB memory region. So after that, it will register this 1 GB memory region on the RDMA communication. And if the host machine needs more memory, it will evict this 1 GB memory region. So at the daemon side, the memory is always managed at this scale, 1 GB.
Okay, so there is no defragmentation.
Yeah, we have no question.
I'm Akshay Narayan from MIT. I'm wondering if you evaluated on applications with high memory bandwidth utilization and what performance you saw if you did.
Sorry, can you repeat your question?
If you evaluated on applications with high memory bandwidth utilization.
High memory utilization?
Yeah.
High memory bandwidth utilization.
High memory bandwidth. Currently, I think the two applications we run, the super-sensitive application, they should require relatively high memory bandwidth, relatively high memory bandwidth. Yeah.
And what performance degradation did you see in that case?
What? Sorry.
Application performance degradation did you see in that case?
Sorry, I haven't got your opinion.
So in the applications that had high memory bandwidth utilization, what performance degradation did they experience?
Oh yeah. So in our evaluation, you can see for those throughput-sensitive application, our memory disaggregation system, Infiniswap, can maintain its performance around 60% for power graph. For the GraphX, the remaining performance is just a little bit higher than the disk case. Yeah, so we have some remaining issues in this part, and in our future work, we are also trying to remove this bottleneck.
Okay, thank you.
Okay.
Hi. Here.
Hi.
Harry Liu from MSR. So is there any evaluation about how much CPU you trade for this Infiniswap? Because I saw that you are using one-sided operation, and typically it requires CPU while loop to see whether the data is ready, and when the number of applications is large, so whether you are wasting a lot of CPU.
Okay. Yeah, thank you. We did measure the CPU usage at the remote side, which is the demo side, but actually we haven't measured the CPU usage on the block device side. But based on our experiments, the CPU usage should not increase too much, because we want the Infiniswap will periodically check the block device will periodically check the activities on those only always swap space, but in general it's not a busy checking, it's periodical, so we haven't increased the CPU usage too much. Okay, thank you.
Hi, Marius from APFL. Nice work.
Thank you.
So I have actually two questions. The first one is about the swapping system, the Linux swapping system that you built upon. So I guess this system was built having in mind that it's backed by slow magnetic hard drives. So
yes.
I speculate that it's not well optimized, and you're using this in a setup that you demand very high performance out of it. So did you observe any kind of bottlenecks because of this system?
Yeah. So as I mentioned for this graphics, so in one graphics running, the local disk will be the bottleneck of our system. So, and in our future work, we are trying to remove this local disk, to remove this bottleneck by using multiple remote data replica.
No, actually, I meant the kernel code that is in charge of swapping, but we can take this offline. And my other question is that it's pretty common nowadays that applications use huge pages that they're not swapped out. So how do you see your system fit in this setup?
Currently Infiniswap does not support huge page. Yeah, but it's one of our future work.
Okay, thank you.
Thank you.
Last one.
James from NetApp. So I just have a quick question about your hardware setup for the testing. So the local disk, was it a magnetic drive or was it an SSD?
It's a magnetic disk.
Have you evaluated this with the swap being on an SSD, because they can provide access latencies, especially random ones that are order magnitude or two faster than magnetic disks?
Yeah, that's a very good question. So because of the relative limitation for SSD, I think it's not very commonly used as a swap space. So we haven't comparing Infiniswap with SSD. Yeah.
It seems, since the access latencies are somewhere on the order of hundreds of microseconds as opposed to 10 milliseconds or so, it seems like it could be a good comparison, because you might be able to reclaim a lot of the lost performance just by switching to SSDs as opposed to going over the network and using RDMA.
Okay. Yeah. Thank you.
All right, let's thank Juncheng again.